In this segment, we'll talk about a worked out example from chapter 3, which is micromechanics of composite materials. Let's look at what the problem statement is. So the problem statement is that, hey, you need to show that G12 is Gm divided by 1 minus Vf if the shear modulus of the fiber is much, much greater than that of the matrix, which is true for polymer matrix composites, graphite epoxy. And the second part of the problem is to show that G12 is equal to this expression here, which is different from this one, as you can see. But this is using the Halpin Tsai equations. And you're going to assume that the fibers are circular, packed in a square array, which means that the xi, which you're going to use in the formula for the Halpin Tsai equation, will be equal to 1, because that corresponds to this one. So that's why this packing geometry is given to you. So let's go and see how we can do these problems. So if you look at part A, we have from our mechanics of materials approach, we have this formula, the inverse rule of mixtures. So this is the inverse rule of mixture. So what we're going to do is we're going to simplify this formula. We're going to say, hey, this is GF, this is GM, and this will be VF GM plus VM GF right here. And so that gives us G12 is GF GM divided by VF GM plus VM GF. And this might give us a good feel that, hey, how we should go up and approach the problem, because we know that GF is much, much greater than GM. So somehow we have to use that information, which basically tells us that hey, GM by GF is approaching 0, as GF is much, much greater than GM. So let's go and take advantage of that. So what we're going to do is G12. We're going to divide both sides by G, both the numerator and denominator by G, GF. So we'll have GF GM. We're going to divide the numerator by GM, GF, and then we're going to do the same thing here. We're going to say VF GM by GF plus VM GF by GF. So we're dividing the numerator as the denominator by GF. So this and this cancels. This and this cancels. So we have GM divided by VF GM by GF plus VM here. And as was you're seeing that here, this one here is going to be a very small quantity here as compared to, so this quantity here, because VF is somewhere between 0 and 1, and since GM divided by GM is a much, much small quantity, it will be much smaller than VM itself. So we're going to get GM divided by VM as the approximation here. Maybe we can call it an approximation. And that is nothing but GM divided by 1 minus VF, because the volume fraction of the matrix is simply 1 minus the volume fraction of the fiber. So that is the derivation for calculating G12 from the mechanics of materials approach. If we have the modulus of the fiber to be much, much greater than the modulus of the matrix. Let's go for part B. So we already know that G12, this is part B, G12 by GM is equal to 1 plus xi neta VF divided by 1 minus neta VF, where neta is given by GF by GM minus 1 divided by GF by GM plus xi. And as you can see that if GF by GM is much, much greater than 1, you can see that neta will be GF by GM, because it's much, much greater than 1 approximately. And GF by GM will be greater than xi. Xi is 2 for our, xi is 1 actually. So xi is equal to 1 for circular fibers in a square array for G12. So we can very well see this will be equal to 1. So neta is approximately equal to 1. So if neta is approximately 1, Xi is equal to 1 because we have that for our circular fibers in a square array. So that gives us G12 by Gm will be equal to 1 plus Xi is 1. That is because of the Halpin Tsai equations, what Xi is. And then neta is 1 because Ga by Gm is much greater than 1. And then you have Vf, and then you have 1 minus 1 times Vf right here. So what you're going to get is G12 is equal to Gm times 1 plus Vf divided by 1 minus Vf. So that is the formula which you get for the value of the shear modulus in the 1-2 plane if you're using the Halpin Tsai equation. And that is the end of this segment.